So welcome everybody. I'm very happy to be here. I want to thank Jimmy for organising this conference and for inviting me. I'm honoured to be a speaker at his conference. So what I want to do is talk about some of the history of language-oriented programming, the idea, where the idea came from, and how I see it working, and a bit about how I've used it in the intervening 25 years. So, cast your mind back, those who have been around that long. 25 years ago, Windows looked like this. I found this slide on the internet, this image, and only recently noticed the little thing at the bottom that says the C drive has 477 megabytes free out of 498 megabytes. For the youngsters, a megabyte is 1,000th of a gigabyte. So there you are. Linux had been out for a few years. The Linux kernel had just been released, and that's what Linux looked like. My desktop looks very similar to that now, actually. The web had just come out. The Mosaic, the world's first web browser, had just been out for a year, and that's what that looked like. Don't see anything wrong with that. My home page looks very similar to that. Actually, my home page has been out since 1995, and has hardly changed in the inside. So what's happened since then? Well, computers are many times faster, orders of magnitude, thousands of times faster. And they've got thousands of times more memory and disk space. And as a result, we're able to develop much bigger and more complex systems, vastly more complex, much bigger systems. And the computer systems have become more ubiquitous. Everything, computers are everywhere now. There's one in my pocket. I suspect you've all got one, or perhaps several, with you at the moment. So what does that mean? It means that language-oriented programming the need for it is greater than ever. It's more relevant than ever it was even 25 years ago. So where did this idea come from? Back in the 1990s, I was a young researcher at Durham University, researching software development methods and looking at trying to bridge this abstraction gap between computer languages, computer code on the one hand, and applications on the other hand. So we want to develop an application, we've got a computer language, we want to write some software to bridge the gap so that this computer language can now implement this application. How do we bridge this gap between these two? And that idea of the abstraction gap is quite important. And as you can see, if your computers are getting more powerful, got more memory, you want to develop more complex systems, that gap is getting bigger and bigger. And that's why I'm saying this language-oriented programming is more relevant than ever. So some of the methods that I looked at in my research, one was top-down development, stepwise refinement. I expect you've all heard of that. So the idea behind that is we start with the high-level design documents, we produce specifications, we refine the specifications into a high-level design, and then refine that into a lower-level design, all the way down. Eventually you get to something which you can implement directly in code, and then you start writing code. That has various problems. It works really well for a nice small self-contained problem where you can hold everything about the problem in your head at once and see the whole development process kind of unfolding. If you've got a really big system, then that breaks down. You can start writing specifications and you can start refining them, but actually how do you know you're actually making progress? It's not always obvious that you're making progress. And I've seen that in some systems, particularly object-oriented systems, I think fall foul to that you have layer after layer of abstraction where you're not actually making any significant progress towards the solution. So you end up with objects and methods that take some data and tweak it a little bit and then pass it on to something else to do all the real work. And the next thing just fiddles with it a bit and passes it on to something else. So that's top-down development. Then there's bottom-up development, where you start with code. So you start by writing some code. You write some library utilities, some low-level code. Then you combine those into higher-level code, and then into higher-level code, and eventually you've constructed a complete system. So with top-down development, one of the other problem is until you've actually got to writing some code, you can't test anything. So any bugs or design errors that you've introduced at the beginning, you'll never find those until you get all the way to completely finishing the system and then find, we've made a fundamental error in our design of the system, it's not going to work. Bottom up, at least you can start testing, but again, it's difficult to know if you're really making progress towards the application that you want to develop. Then, around that time, I also discovered there's this, what I call outside-in development, which is a combination of top-down and bottom-up. And I discovered this by chatting to a programmer who worked for the military. And she was saying, well, we have the high-ranking officers, they all get together and they write the specifications. And then the lower ranks, they're the programmers, they write the code. Now, of course, the high-ranking officers are all very busy people, so they takes them a long time to get together and write their specifications, and we can't have these lower ranks just sitting around doing nothing, so we've got to give them something to do. So while these people are writing the specifications and designing the system, we'll get these people to write some code. Yeah. And so everybody's working, so it's more efficient, you see. So you have this top-down design happening and the bottom-up implementation, and I hope that they somehow meet in the middle. Yeah. So I think you can see that this outside-in development combines the worst properties of top-down and bottom-up in one neat development method. So then looking at this pattern, to my researcher mind, I thought, hang on, there's something missing in the pattern. There's symmetry says there's a step missing. And the addition to the set would therefore be something you'd call middle-out development. What is middle-out development? What does that mean? What does it mean to start in the middle of the abstraction gap between code and application and work from there? That's what the first thing that you're going to do is jump into the middle and do something there. And that's took a little while to think about. But then the key insight came that the middle layer between code, low-level code and application, the middle layer is a high-level domain-specific language. And I hadn't come across the term domain-specific language at the time, so I just called it a language in which it's easy to write the kind of system that I want to write. So your first step, before you do anything else, is design the language. So that's the first step, design this high-level domain-specific language, a language in which it's easy to write this kind of system. And then you can, once you design that language, you can then implement a compiler or an interpreter for that language, so it then becomes an executable language, not just a design, and you can then implement the new system in that language. And as Jimmy said, when you do that, because this is a language in which it's easy to write that kind of system, this implementation is so much easier, so much easier. It's an order of magnitude less code that you have to write to start with. And it's understandable code because it's domain specific. It uses the terminology of the domain. It uses the concepts of the domain. It is understandable to people from that domain. So even they can write that part of the system themselves. And I'll talk about that a bit in a minute. And if you do your design properly, the design of your language, you formally specify it, so you use mathematics to pin down precisely the specification of the language in its syntax and its semantics. Then the steps 2 and 3, the implement the language and implement the system using the language, those are completely independent steps. So, because the language is the part that connects them together, and that's fully specified. So I started writing a paper called Middle-out Development. And after a while I thought, you know, this term middle-out development, if you say it to somebody, it doesn't mean anything to them. And even in the context, as we just said, of top-down and bottom-up and outside-in development, middle-out development is still not very meaningful. And I thought, well, actually, the key insight is the development of the language. So the language is the key part of this. So I coined the term language-oriented programming. That's because the starting point is going to be the language. So I have an analogy now to talk about how this all fits together. You're bridging an abstraction gap, okay, between two places. You want to build a bridge between two places. Top-down developments, you start at one end, at the top end, and you start building a bridge. And I hope that eventually you'll reach the other side and you'll be able to get across. That's bottom-up development, you start at the bottom end, the code end, and you start building a bridge from that end. And then eventually hope you reach the other side. And outside-in development, you're starting from both sides and hoping that you'll manage to patch them up and get them to meet somewhere in the middle. And in this context then, what's middle-out development? What's language-oriented programming? Well, language-oriented programming, you start by putting down a pier or a column or something, a piece of solid ground in the middle between the two. That's what your language is. That is a piece of solid ground, and it divides the task into two. And it doesn't divide the task into two halves, because as you'll all know as software developers, the bigger your system is, the bigger that abstraction gap is, the bigger the problem is. And that doesn't scale linearly. It's probably not even quadratic, it's probably closer to exponentially difficult. So if the gap's twice as big, then it's 10 times harder. The problems that you get, the amount of code that you need to write, the number of bugs that you have to fix, the time that it takes to implement is an order of magnitude bigger. So by putting this piece of solid ground in the middle, this language, you're dividing the task into two tasks that are a tenth of the size. That's got to be a win, hasn't it? And as I was thinking about this recently, I thought, yeah, this is not just bridging a gap, an intellectual gap between two intellectual domains of application domain and the source code domain. It's also bridging a gap between groups of people, between software developers who are on this side, who know about code, and the domain people, the users, the domain experts on the other side. And what this language-oriented programming is giving you is a piece of common ground in the middle, which is in neither domain, but it's in both. And it allows the people to talk to each other in a common language, so that it's familiar to programmers because it's a programming language, but it's familiar to the domain people because it talks in terms of concepts they know, in terms of domain concepts, in terms of the things that they're familiar with, concepts, the data structures, the functions. So your domain-oriented language takes for granted all the things that they take for granted and hides away all the details of the things that they don't have to focus on, that they hide away, and so on. So language-oriented programming, it's not just a convenient way to write code, but it also creates common ground between people. It bridges the gaps between people, and that's something that I've been trying to do all my working life as well, because I've had one foot in academia and one foot in the industrial world for all my working life. and trying to bring these two groups of people together and say, look, you've got a lot to learn from each other. You've got a lot to share with each other. So I've been building bridges all my life. While I was working on this, I came across this quote by Alfred North Whitehead, who is a mathematician who lived long before, I forgot to look up his dates, but it's a long time before the development of electronic computers. He's talking about mathematics notation, and says that by relieving the mind of all unnecessary work, a good notation sets it free to concentrate on more advanced problems, and in effect increases the mental power of the race. So if you only take away one idea from my talk, then I think his idea is the one I want you to take away. This isn't just a neat way to develop programs quicker. It's not just a way of bringing people together, but it's a way of doing things that couldn't be done before. It's a way of solving problems that you literally could not solve before. It's a way of thinking thoughts that you literally could not have thought before. By inventing a new language, you have the ability to think things that you could not have thought of before. That's enormously powerful. It's also enormously difficult. I don't want to underestimate the difficulty of developing a good domain-specific language. The difficulty is high, but the rewards are so much higher, so much higher. An obvious reward is once you've developed your language in which it's easy to write this kind of system, of course it's easy to write that system that you wanted to write, but any other system in that domain is also just as easy to write. So you've not just developed a way to develop this one system, but all these other related systems are also now easy to write. You can imagine that middle ground being shifted into closer to one side or the other side, and if it's really close to the application side, what you've got in effect is a very high level domain-specific scripting language in which domain experts can just go in and write programs for themselves just by writing a few lines of code, because it's all using all the concepts that they're familiar with, and just by writing a few lines of code they can implement a whole new system. That's really powerful as well. If your gap is really huge, then of course developing the language might itself be a big problem, and developing the system might still be a big problem, but of course you can use this method recursively. So you can put some extra peers or columns in the middle and use the domain language-oriented programming method recursively to use language-oriented programming to develop the language, or implement the language, rather. So, that's some of the advantages, some of the challenges. What are the requirements? What makes a good domain-specific language? One thing I've already mentioned is it has to be, if you think of the pier in the middle of the river, it has to be firmly grounded, absolutely solid ground that everybody can rely on. And to do that means it has to have a complete formal definition, using formal methods, which means that the syntax and semantics are completely precise, formally defined. They're concise, they're precise, they're unambiguous. That definition has to be such that the programmers can understand it if you teach them about the domain, give them some training in the domain. The domain experts can understand it because it's in their domain, but you need to teach them about how your semantic definitions work so that they can read it. And it's quite possible to teach people how to read formal methods, formal specifications. It's a lot easier to read a formal specification and understand it if you're familiar with the domain than it is to write it from scratch. So they don't have to be mathematicians to be able to read the formal specifications. if it has that definition, then that decouples the language users from the language implementers. That allows you to completely change the language implementation if you need to. If you want to move to another platform, you can just unplug one language implementation and plug in a new one, and everything works perfectly first time, no bugs. If you one trap that's enticing you to fall into is to say, well, I'm going to implement my language in this language, so why don't I just make the features of this language available just in my domain language, because that costs nothing. It costs nothing to make the features of the underlying language available in your DSL. And that's what I call allowing the implementation language to leak into your DSL. And so it costs nothing to do that in terms of programming, but in terms of keeping your domain-specific language definition concise, you've suddenly exploded it by adding the entirety of the C programming language, or scheme, or whatever your target, Java, whatever. You just added that, the entirety of that, to your definition of your language, and you've made it that much bigger. So the cost is actually enormous if you think of it in intellectual terms, in terms of how you've exploded the size of your definition. Now that's something you want to avoid. So one exception to that rule is if it's a small domain-specific language that's an add-on to an existing language, then obviously you're going to keep all the existing language and you're going to add on this extra domain-specific piece onto it. But in a big system where you're developing a new language from scratch, you don't want this leakage to happen. So developing a domain-specific language is a challenging problem, as I said. How do you do it? The problem is that programmers don't understand the domain, so they don't know what to implement, and domain experts don't really understand programming, so they don't know what is possible to implement, and they can't provide a useful specification for the domain-specific language. That's inevitably going to be a problem, because what we're talking about is developing something which allows us to do things that have never been done before, that allows us to think thoughts that have never been done before. Obviously, it's going to be a non-trivial task to do that. But like I say, an enormously worthwhile task. So it's going to be an iterative process. You want to listen to your domain experts, get them to talk about the domain and talk about how things work in the domain. Learn about the domain from your domain experts. Capture their domain knowledge in the form of a language. So, then you can ask them, how would you describe this process that you want to do? How would you describe how to do that to somebody else who's familiar with the domain, but not familiar with that particular process? So, writes out a procedure for how to do it. Write some pseudocode or whatever, and just write out how you do it. And you look at the words that they're writing, look at the concepts that they're using, look at the terminology, and try and put all that into your language, so that what they're writing in effect becomes an outline of how the domain-specific language is going to work. Take their concepts and generalize them and add some more programming concepts, ideas from programming, because they might not know much about programming and how programming works. They might not know about ideas like lists and sets and recursion and all those useful programming stuff. So you can add that to the language and talk to them and describe that to them. Yeah, something I forgot to mention. This problem about domain experts and programmers not understanding each other still is a problem, even when those two groups are the same person. It's true. That's my experience anyway. And I'll talk about that in a minute. Yeah. It's true. So you can then incrementally improve the language and say, look, hey, we've got this prototype of a language, and that process you were talking about, this is what it looks like as code in our new language. And this is the precise formal definition of that code. And then they'll say, but you forgot this particular case. your interpretation of that function is incorrect. And so you iteratively improve it. So as I was saying, a new language makes possible new thoughts and new ideas and increases the mental power of the language users. You're increasing the mental power of the human race. Yeah. Let's not sell ourselves short here. But to do that, it's going to take a little time to do that. So, how have I used the method of language-oriented programming? Well, after doing this research, publishing the paper and sending it off and waving goodbye to it, and not kind of trying to publicize it or anything, I went back to doing other research, and the area I was researching into, which is transformational programming. So program transformations is an area that I've researched in my whole life. A program transformation is any operation which takes a program and changes it in some way and produces another program where you can guarantee that those two programs have the same semantics, the same function, they're functionally equivalent, they have the same external behavior. And I developed this idea of, so you can take a specification, which is a precise definition of the program that you want to implement, which says exactly what you want to do, but doesn't say how you want to do it. You can refine that specification into a program, into executable code. If each of those refinement steps is a transformation, then you can guarantee that that program correctly implements that specification, and that's guaranteed by construction. You don't actually need to prove the correctness of your program. The correctness of the program is guaranteed by the process by which you've constructed it. And that's the idea behind transformational programming. That's an idea that I've been working on for 30 years or more. The idea has actually been around since the 1970s, but required a lot of development of the theory of program transformations to make it into a practical idea that can actually be used. So here's how it works in practice, that you start with a formal program specification which doesn't say anything about how you're going to implement it, but you have some vague informal ideas about how you're going to implement it. The ideas that you have guide the transformation process, and so they guide the way you select transformations. And you transform the program until eventually you get to something which can be implemented directly in code, and then there's your program. And I wrote a paper about this, published fairly recently, on provably correct derivation of algorithms. So this method is a practical method for deriving complex algorithms. It scales up to large programs. The programs that you develop can work first time, and you'll see an example of that if you read the paper. I won't go into that. You don't need to invent loop invariants. You don't need to verify correctness of the code. It's guaranteed to be correct, and it produces efficient implementations. So, why I'm talking about this? Well, one reason is throw out an idea for your next conference, maybe. I'll just throw that out. But also, the main reason is to do this research, I needed a system for transforming programs. I needed a program transformation system, an engine for program transformations. So we developed a prototype of this program transformation system, and we decided to call it Fermat, which is after Pierre Fermat, the mathematician. Interestingly enough, a few years after we developed the system and called it Fermat, Fermat's last theorem was proved. The proof was called Riemann conjecture, and we'll just see what happens. Yes. So the initial prototype of a transformation system was implemented in Common Lisp in the late 1990s. And I realized that this was going to be a good case study for language-oriented programming. It's a really big, messy, complicated system. What we really want, I thought to myself, is a language in which it's easy to write program transformations. So I developed the language WSL, which is wide spectrum language, which is the language that we are transforming. It's wide spectrum, so it has high-level abstract specifications and very low-level programming constructs all in one language. So all your transformations take place within a single language, all the way from high-level specification all the way down to low-level code. That's all. It's very convenient because everything happens within one language, everything happens within one theory of program transformations. You don't have theories about how to translate from specifications to code. Everything is code, in effect, even your top-level specification. So that's WSL, that's the language that we're transforming. So then I developed, extending on top of WSL, MetaWSL, which is a language for writing program transformations. And I did that by looking at the code that we'd already written and saying, well, there's these patterns that are appearing over and over again. It's big chunks of code that you're writing over and over again in different ways. They're different enough that you can't make them into a procedure or a function, but they're very similar. So I want to put that as a construct, a basic level construct in the language. So for example, when you're transforming a program, often you want to go to every statement in the program that you're transforming and do something at that statement. Look for a pattern at that statement. So we have a looping construct which is for each statement, or for each expression, or for each condition. You can loop over all the statements, expressions, the conditions in the language. Often you want to say, well, if your program looks like this, then swap it around and change it to look like this. So that's a pattern match and a replacement. So that's a fundamental idea in program transformations, the idea of a pattern match and replacement. So that's the fundamental to the language, the MetaWSL language. And the MetaWSL language doesn't just have looping constructs and pattern matching, but it has looping constructs that understand the syntax and the semantics of programming. And it has pattern matching that understands the syntax and semantics of programming. So a load of implementation details are all hidden away. As a result, writing a new transformation might take just half a dozen lines of code, or a dozen lines of code, and you've got a complete new transformation that you've written. Whereas before it would take pages and pages and pages of Lisp or C or whatever your implementation was. And it would have bugs in it, and you'd have to test it and fiddle with it and try and get it to work. And whereas, half a dozen lines of code, you can just look at that and say, yes, I know that works. That's so obviously correct. So I developed MetaWSL, the language, first, and then developed an implementation of that. And that was originally in a language called LaLisp and the Concerto case tool builder, which have long since fallen into obsolescence. So a few years later, the whole language was re-implemented. So I wrote a MetaWSL to Scheme translator, and of course that was implemented in MetaWSL. So then I could bootstrap the whole system into Scheme. And that would have been a much easier process, but in the process of developing, implementing MetaWSL and using it, we'd allowed some features of LaLisp to creep in to the language, and they all had to be plucked out one at a time so we could move it onto Scheme. So that made the job of porting it so much more difficult than it could have been. But it wasn't too bad, it wasn't too difficult. But it could have been a lot easier if we'd realised that we had to be really rigorous about fully specifying what we mean in our language and not allowing the implementation language to creep in and say, well, this means whatever it means in the implementation. Can't do that. Not if it's a big system like this one is. So the current system, which I've been working on for all these years, the transformation engine consists of about 3 megabytes of MetaWSL source code. And then when we translate that into the Scheme language, that expands into 5.5 megabytes of Scheme with lots of macros in there. So when you expand all the macros, it expands into 12 megabytes of Scheme source code. And then we have a Scheme to C compiler, so we eventually get to executable code via Scheme to C, and that compiles the Scheme into 16 megabytes of incredibly complex C code. I was saying incredibly complex, so that's... I just dived in, picked a random file, and picked a random chunk out of the file to put into the slide. This is the C code that you get out of. I'm talking incredibly complex here. And if you look very carefully, you'll see it says if at the top, and there's a curly bracket at the bottom. Yeah, this is just one condition in an if statement. And it's all on one line as well. That's why I've described in this slide, I've described it in terms of megabytes of source code rather than lines of source code. Because in the C, there might not be that many more lines, but they're like thousands of characters long each line. So, so lines of code doesn't really get across the difference. So there's an order of magnitude difference there in the amount of code that you've got, but there's also an order of magnitude or more difference in the complexity from this nice simple stuff that you write in MetaWSL that's really simple and easy to understand. And if you're interested, you can go and download the papers on the transformation system and look at some MetaWSL code, which then compiles into this massively complicated C code. So this Fermat transformation system is currently being used in a number of research projects around the world, investigating different aspects of languages and transforming systems. There's a guy who's taking compiled Java code and decompiling it back into source code using transformations, transforming. And there's a number of other projects that are using it. It's also used by the company that I work for, which is Software Migrations Limited. And what we do is take assembler code on IBM mainframes that's been written by assembler programmers over many decades. And we take that assembler code, we translate it with a translator directly into very low-level WSL code. This is really low-level stuff that captures every detail of that assembler program. And then we're within the transformation system. So then we apply thousands of transformations to every assembler module. Typically 3, 4, 5, 10,000. For bigger modules, it'll be 100,000, 500,000 transformations are applied. And that produces high-level, structured, understandable WSL code, which then gets translated into the target language. And because this is they're typically large financial organizations that are using IBM mainframes, so their preferred target language is typically COBOL, because that's the snazzy new language for them. You know, they want to get their crusty old ancient assembler code that they're finding it difficult to find assembler programmers for, and really finding it difficult to maintain, and move it into the new world, which is COBOL. Yeah, IBM COBOL as well, not modern COBOL. Yeah, that's what the customer wants. So kind of we take our nice, beautiful, highly structured WSL code, and then we have to kind of force it into the COBOL mold. So we have to transform it a bit more to make it, and we force COBOL to do things that it was never designed to do in the first place, to get those two to fit together. But you know, looking at that task, that's an incredibly complex task, to take something that was written by assembler guys who sometimes they go right down to the bare metal. They know this machine inside out. They do self-modifying code. Yeah, I'll overwrite this branch instruction with another branch, so the condition on the branch instruction changes. Yeah, we'll do that. I'll pull out a value from a table and use that to overwrite an instruction. What? I'll branch to an offset of this instruction. I'm going to branch minus 18 bytes. They do that all the time. Yeah. They have this thing called an execute instruction, which says, go and load this instruction from memory and then fiddle with it. And with the value, put stuff in the value of the register into the instruction that you've just loaded, and then execute the result. So these are all the kind of surface level complexities that we have to deal with just to translate the assembler into something that captures the behavior of the assembler. But then that's massively unstructured code. You know, you don't have subroutines in assembler. Well, the way you implement a subroutine is you say, save the return address, which is the address of the next instruction, and then branch off somewhere. And then I might save that return address somewhere, and then eventually I'll load it into a register and do a branch to register instruction, which will take me back to here. And that's how you do subroutines in assembler. But of course, there's nothing to stop you overwriting that return address with a different return address, or branch from the middle of that subroutine to the middle of another subroutine, or branch out completely and go to an error handler. So our system has, by transforming the system, we have to follow everything that's going on in there and restructure it and get a nice clean, self-contained procedures out of that, which we're actually quite successful at doing after 20 years of working on this stuff. We're getting quite good at it, I have to say, if I say so myself. But this task is so complex, you could not imagine trying to develop something to do that in a programming language in Java or in C. Well, I couldn't, certainly. You couldn't imagine one person being able to maintain the entire thing as a part-time job, which until recently I was working part-time for software migrations, maintaining these assembler, the Fermat migration system, and also working part-time as an academic, as a reader in software engineering, doing research. That was possible to do that. It's only possible to do that because of the MetaWSL language, because we used language-oriented programming. So, in conclusion, that's good timing. Just want to emphasize the tremendous difficulty of the task that you're facing, but also the tremendous rewards. And the rewards are kind of tremendous squared compared to the difficulty. They're massively greater than the difficulty. How you can, but that's, even though this is a difficult task, it's a doable task. You can do it if you approach it with the right mindset and in the right way. And Edgar Dijkstra wrote in his essay, The Humble Programmer, he was not talking about language-oriented programming, he's talking about programming in general being a tremendously difficult task. But his words definitely apply double to language-oriented programming. That will do a much better programming job provided we approach the task with a full appreciation of its tremendous difficulty. So because the task is tremendously difficult, we must stick to modest and elegant programming languages. That's how you manage that level of difficulty. That's how you manage complexity, is by making the language that you're working with small and elegant and understandable. And unfortunately, most existing programming languages, I think that's me, sorry. It's not me. Oh, it's my ring. Oh, yes. So, if you stick to modest and elegant programming languages, if you respect the intrinsic limitations of the human mind, and that means being humble, approach the task as very humble programmers. Acknowledge your own limitations and say, I'm only human. Mind has its limitations, and therefore I need tools that are very simple and elegant and completely precisely defined. But if I do that, then I can make my mind bigger. I can achieve greater things than I would have even thought possible. So, and over 25 years of using this method, I found that to be true. And so I just want to throw it open to questions now. That's my conclusion. Yes.
Could you use this to simplify, if you have a complex system,
Yeah.
could you use this to simplify code in the same language?
In the same language.
So like you have a bunch of code, like it's complex, and then you apply transformations on that to simplify it
Oh
in
yes.
the same language.
Yeah. Yeah. So if using transformation system, you mean? Yes. Yes. So you can. The source and the target language can be the same language, and you can take code that's very complex and you can restructure it, you can simplify it. I mean, that's, in a sense, that's easier than going from assembler to COBOL. So we do typically simplify the assembler. So looking at McCabe complexity, which is the standard complexity metric, it's typically reduced by a half, reduced to half when we've done all the restructuring and simplifying. So yeah, you could use this on existing code. You just need translators into WSL because the transformation engine works on WSL.
Oh.
So yeah, if you can translate your language into WSL and back out again, then you could pull it in, do all this stuff onto it, and then spit out really nice, elegant, clean, simplified code that's guaranteed to be equivalent to what you started with. So if you're, as I said, if you're applying thousands of transformations to a program, and 10,000, 20, 30,000 transformations, each of those transformations is 99.9% likely to be correct. By the time you've applied 10,000 of them, if you do the mathematics, the chances of your program still working at the end of the process is actually quite small. That's why you need a program transformation theory in which you can guarantee 100% correctness for those transformation steps. You still have to implement them correctly, of course, there's still that task, but we find, we're routinely applying thousands of transformations, tens of thousands, hundreds of thousands of transformations and getting code out that performs exactly equivalent to what we're putting in. So, any more questions? Yes.
So is this WSL language, is that like the intermediate code in a regular compiler?
Yeah, it's similar to that, yes. It's
maybe more powerful or more formal, or?
It's definitely more formal, yes. It has formal definition. So it's an intermediate language but it's because it's wide spectrum, it can cover the whole range. So you can take your very low level stuff and express it directly in WSL. And then you can transform that into some high level stuff that it goes directly into high level language. So the translation steps are very simple. They're basically line by line translations. All the real difficult stuff, all the clever stuff happens within the WSL.
So for implementing a decompiler, for example,
Yeah.
would be
Yeah.
suitable.
Yeah, so a colleague of mine is doing research on decompiling, and they're using WSL to do that. So you take your low-level code and you apply transformations to it, and we've invented some new transformations that do things like finding where you're putting parameters on the stack and turning that into actual parameters, those kinds of things. Yeah. Yes.
What advice would you give on when not to apply language-oriented programming? When should you not?
When should you not do it? Yes, of course.
You're too small.
Yeah, if the system is small, then there's no real advantage to, if you're hopping over a small stream, there's no real advantage to building a big island in the middle of the stream, because you can do it in one step anyway. If there's an existing language that you can use, then that's not quite the same thing, because you're still using domain-oriented programming. Anybody else? What would you think?
Yeah,
I'd say you use it's the obvious thing to use, and why doesn't everybody use it all the time? Unless they're developing really small pieces of code, why don't you use it all the time? Yeah. Well, then I would say that, wouldn't I? Yes.
when we're talking about a domain here, I mean, if we say that banking is a domain,
Yeah.
could every bank use the same language?
Yeah.
Or would it be this bank's language would be different from another bank
Yeah.
because of reasons?
Reasons, yes. That's a good question. You know, and when you develop these new languages, what do you do with them? Do you keep them to yourself because that gives you an edge over your competitors, or
Sounds like
do you share them because
companies usually do.
yeah, do you share them because that everybody benefits then? And if everybody shared their languages, then the whole human race would benefit. Yeah, there's something to think about, and maybe there's a compromise between the two where you keep it to yourself for a few years, and then when you've got all your commercial benefit from it, then you start sharing it with other people as well, so that the rest of the human race can benefit. Which is what we did in Software Migrations Limited with Fermat WSL. So the Fermat transformation system is I persuaded the company that it would be a good thing to do to release it to the rest of the world. So it's available to anybody to pick up and use. You can download it from my website. There's a nice graphical front end on the transformation engine that a PhD student of mine wrote. So you can actually play with transformations without having to understand all the mathematics and the theory behind it. You can see a piece of code and click on it and apply a transformation and see what happens to it in the graphical front end. And yeah, it hasn't affected us. In fact, it's benefited us as a company commercially, because we can say we developed this thing that's out there that's being used by all these academics, that's had all these papers published on it. It's not just a load of snake oil. You can trust what we're saying about what our tools can do, because these papers have been published about the basic technology. So we benefit from releasing it in that way. So there's certain parts that we keep proprietary that are to do with how you translate assembler, but that's fine for keeping that